Well, thank you for having me again. My name is John Fragala. I'm a principal architect with Xyratex, and today I'll be talking about improving Lustre OST performance, leveraging a new technology that's been developed by Xyratex called GridRAID. So before I talk about what exactly is GridRAID, what is the problem we're trying to solve here first? The problem we're trying to solve here first is the long extended periods of rebuilding a failed drive in a file system or in a RAID distribution or RAID block. So for example, a 4 terabyte drive under a standard rebuild rate of, given number, could take days, depending on how much balance you put in front-end performance for applications versus back-end performance of trying to rebuild that failed drive. You look at the future, we're looking at 5 terabyte drives, 6 terabyte drives, 8 terabyte drive. That problem is just going to be exponentially worse if we go down the traditional path of leveraging a standard RAID 6 type data protection layer. So what is the new approach here? Is that supercomputing in 2013, Xyratex announced something called GridRAID. It's a new data protection layer to decrease the overall time to repair or rebuild a failed drive in a volume group. So if you compare that to a traditional RAID 6 rebuild time, GridRAID will reduce the amount of time you're spending repairing a failed drive by 4x. What does that mean overall? That means overall is that you don't extend the period of time repairing a failed drive in RAID 6, which means affecting your application performance trying to access read-write data of that volume that you're trying to rebuild data, that you actually will reduce the amount of time of a degraded state by 4x leveraging GridRAID. So what exactly is GridRAID? Next slide, I'm just going to read exactly what a quote is. So GridRAID is ClusterStore's implementation of parity declustering RAID. I'm just going to read the quote out loud. So parity declustering is designed to balance the cost against data reliability and performance during failure recovery. So GridRAID is a implementation of a new data protection layer based on a parity declustering algorithm to reduce the amount of time spent of repairing a failed drive compared to traditional RAID 6. So how do we implement GridRAID? So GridRAID, you take the same block devices that you have in a volume group, and you still have your data protection stripe, let's say 8+2 like we know and love today, but instead of leveraging the physical drives as your stripe count, you actually create a parity declustered leveraging GridRAID to create a stripe across the multiple logical devices. So the GridRAID replaces the algorithm of RAID 6, but still leverages the stripe count of RAID 6, leveraging GridRAID or parity declustering algorithm implementation. It's basically an algorithm that we introduced to replace leveraging RAID 6, and we just leverage GridRAID as our data protection layer with a stripe of 8+2. We're still as good in protecting your data with 8 data blocks and 2 parity blocks. So when we define a GridRAID, we define tiles. So tiles is nothing new to GridRAID. Tiles exist today in RAID 6. So tiles no more than just how much of number of rows or number of blocks need to be allocated per drive to create a stripe. So today, if you create 10 drives in a RAID 6 8+2, you basically take up 10 blocks, 1 block per drive, to create an integral stripe across those 10 drives. And that is considered 1 tile today in a RAID 6, leveraging 10 drives. Well, you take that same concept, and let's say you apply it to GridRAID. And let's say GridRAID, you leverage only 5 drives, and for this example, our stripe is 3+2. So if you have a GridRAID implementation across 5 drives with a stripe of 3+2, your tile is essentially 1 row of blocks across all drives. Now you take that same concept and you take that same stripe of 3+2, but it's now, instead of only having 5 physical drives, you extend the number of drives to 16 drives. So now your tile, let's see if I get this right, your tile is how many blocks are needed to create an integral stripe across all 16 drives. And in this case, with 3+2, it takes 5 rows to create 1 tile, because it takes an even number of rows. So you have the first rows here is 5, but then you create another stripe of 3 plus 2 and 3 plus 2, and it extends down. And it takes about 5 tiles in this implementation of 16 drives to create one tile in this type of implementation of a 3 plus 2 across 16 drives. So the other benefit of this as well is, why are we talking about tiles and stripe counts and number of rows and tiles? Because each tile is now a dedicated virtual layer that we dedicate to how do we actually repair a drive failure across the multiple tiles. So you can think of this in this implementation is the way that we design a data protection layer of blocks and parities is we actually do a random pseudo algorithm to distribute the stripes and the parities across all available devices in grid RAID. With that, you can think of it, okay, what happens on each tile, and in this example here in this slide, each tile is one physical row. So when you talk about a drive failure, here, in this example here, each tile doesn't leverage the same number of drives to repair that block. So in the first tile, to repair this drive, we actually leverage 4 drives. In the second tile, we leverage only 1 drive. In the third tile, we leverage a different set of drives, and et cetera, et cetera. So essentially, when we repair a physical drive, we're distributing that against multiple tiles, and each tile controls a separate section of the drive to repair that block of that physical drive. So essentially, you're leveraging the entire bandwidth of all available devices in grid RAID to repair a physical drive. Unlike today with RAID 6, when you have a physical drive failure, you're bound by the bandwidth of that one physical drive to repair all the blocks to. In this, you're bound by the entire number of drives you have in a grid RAID implementation of a volume. So compare that to repairing a physical drive, you dramatically reduce the amount of time you spend in repairing a physical drive because of the way you're splitting up the tiles and leveraging what drives are used in each tile to repair that physical drive. And then using distributed sparing, so unlike today with RAID 6, you have dedicated physical drives as your hot spares. So that means when you have a physical drive that fails, you have a new drive that gets automatically incorporated into that new volume, and you start repairing against the volume of that physical drive. With implementation of grid RAID, we actually implement hot sparing or distributed sparing across all the physical tiles. So it's just another block that we actually allocate for spare blocks. So we actually incorporate hot sparing distributed across all available tiles in a grid RAID. So this example here just says for every stripe we do an additional, so for example if we do an 8 plus 2 stripe on grid RAID, we can actually just have another algorithm that says another plus 2 for sparing. So every time you write 8 plus 2, 8 data blocks, 2 parity blocks, we actually allocate 2 spare blocks on top of that as well. So can I hold the questions to the end, please? Column. Yeah, column. Yes. So in the pseudo-random algorithm that we implement on grid RAID, we actually distribute in a tile a dedicated row of spare blocks in each tile. So that means that you could have, depending on how many drives you have in a grid RAID, you could have multiple tiles with multiple spare blocks that you rebuild against too. So this example here, we could extend this if you have, let's say, 40 drives in a grid RAID and you have hundreds of tiles. That means each tile will have hundreds of spare blocks that are dedicated to repairing a physical drive failure. So what does this mean in terms of grid RAID, in terms of actual numbers, for example? So in grid RAID, we don't use the word rebuild anymore because you're not rebuilding a single drive. You're reconstructing the data that's lost in a physical drive, or you're reconstructing the data that's no longer available on a physical drive using the parity and sparing blocks of each stripe across all available spare blocks in each tile, and that's what we call a reconstruction rate now. The reconstruction rate in our implementation of grid RAID and ClusterStor and the rebuild rate is the same value because we leverage MD RAID as the source for data protection in this algorithm here. So if you look at the reconstruction rate leveraging a standard 50 megabyte per second reconstruction rate, the same that you would actually leverage in RAID 6 for a rebuild rate, you could take that same leverage and we could reduce the amount of a recovery time or reconstruction rate. Look at a RAID 6, for example, it'll take approximately 22 hours to rebuild a 4 terabyte drive using 50 megabyte per second rebuild rate. Leveraging that same 50 megabyte per second rebuild rate, leveraging a grid RAID implementation for an OST, you take that same time that you actually reconstruct that data across all spare blocks, across all tiles, down to approximately 5 hours. So you look at this and we expand this to what actually might a grid RAID look like on a ClusterStor OST. So basically each column is a physical drive, each row is a tile, and when we have a physical drive that fails, you could leverage here that all the blue spots are the ones that are being leveraged to repair in the, I would say, the golden blocks. So then that means each row is leveraging a different section of the number of physical drives to repair against all those spare blocks in the gold spots here. So you actually leverage the bandwidth of 40 drives, for example, to repair a single drive failure. And that's where the benefit of decreasing the amount of reconstruction time to repair against all the sparing blocks across all the tiles. So what does this mean for Lustre, right? And why am I talking about so much for grid RAID and reconstruction rate and rebuild rate? What does this actually mean for Lustre? So anytime you've ever run IOR, for example, or any parallel application against a Lustre file system leveraging InfiniBand or 40 gig E, for example, your performance for your application is as good as your slowest OST. So what does that mean? So you could actually have a lot of OSTs being leveraged in parallel, but your time skew and the time you spend executing an application and analyzing data is going to be skewed by your slowest OST because those are that OST is going to service those IOs the slowest because you're balancing out your front-end performance of trying to also reconstruct a failed drive. So if you look at a traditional RAID 6 and you're leveraging an OST, and let's say you have hundreds of OSTs, questions at the end, please. Object storage target in Lustre. All right, sorry about that. My assumption thought you knew Lustre. So with the RAID 6 today, you're going to spend 22 hours rebuilding a drive. That means during a rebuild of a physical drive in RAID 6 today with a Lustre object storage target, you're going to degrade your I/O performance by 45% because you're also balancing out rebuilding that physical drive. Now you could reduce the amount of time to rebuild to dedicate more front-end performance, but that also means you're increasing the amount of degraded state you're in by rebuilding that drive. And the longer you take to rebuild a drive, even though the probability of having a dual disk failure is much lower, and even a dual disk failure in the same RAID group is very low, but you still open that window to increase that probability no matter how small that might be. Take the same grid RAID, and it's very deterministic as well, and you use that same 50 megabyte per second to reconstruct the data across all sparing blocks on the tiles. You take that same degraded state from 22 hours down to 5 hours. So does that mean that during an application runtime, you're only going to affect your application performance if you have days to run this application for only 5.5 hours versus almost a day of degraded state of a single OST. That means that you're quicker to come to a full I/O bandwidth for applications running against and analyzing data on a file system by 1/4 reduction of that time in the degraded state for those OSTs being leveraged in an application runtime versus a RAID 6. And that's overall how you improve Lustre performance, is to make sure that all your OSTs are optimally running at the peak performance, but also you get cases where drives fail, and you actually want to reduce the amount of time you're spending trying to reconstruct a failed drive. So like I mentioned before, your OST is your application or your static synthetic benchmarks are only going to be run as fast as your slowest OST, and leveraging grid RAID reduces the amount of time you're in that degraded state during a failed drive state. So in ClusterStor as well, we actually have these tunable settings. You could actually change the 50 megabyte per second reconstruction rate, and if you're still leveraging RAID 6, rebuild rate. Why do some customers want to change these tuning parameters? Because they want to take the calculated knowledge that I want always to have the most front-end performance for an application, leveraging over clients, leveraging over IB or 40 gig E, and I'm willing to take a longer time to rebuild a single drive failure. So I want to tune that parameter of 50 megabytes per second and take it down to maybe 30 or 25 megabytes per second. But what does that mean to a 4 terabyte drive in RAID 6? You take it down to 30 megabytes per second, your rebuild rate for standard RAID 6 just went from 22 hours close to 35 hours. Take that same value in grid RAID, you're taking that value about 8 hours. But then also, you don't sacrifice that much front-end performance. So now you take that front-end performance hit of 45% degraded performance hit and maybe take it down to 10%. Now your application is still almost running at optimal speed. You take it down even further, that means you're extending the window of trying to rebuild a RAID 6 device or reconstruct the data on a grid RAID device. Now you can set these tunable parameters at a global level, meaning that I want to apply this setting of changing your tunable parameter across all servers exporting Lustre object storage targets. Or if you know that during an application runtime, you have a physical drive that's failed across only one OST, you can actually do a targeted change in that tuning parameter just for that OST, but keep the global level at 50 megabytes per second. And in ClusterStor, we actually have another tunable parameter that you could do for if you, in that case of a rare case of a dual disk failure in a single controller, both rebuild rates will jump up to the maximum rebuild rate, because at that point, you want to make sure that you actually sacrifice a lot of back-end performance and sacrificing front-end performance to rebuild the dual disk failure in the rare cases that do happen. So these are one of the advantages of ClusterStor is you could actually tune these parameters to match application performance front-end and balance the back-end rebuild rate. So benefits for ClusterStor and grid RAID, it just improves the mean time to repair value by 4x compared to RAID 6. You distribute the recovery load across all available devices in a grid RAID versus what you do today in a RAID 6. Your recovery workload is only based on how good your performance is on a single drive. And then with also grid RAID, you can actually reduce the number of object storage targets behind a single Lustre object storage server by 4x. Because in a grid RAID, we still write data stripes of an 8+2. The reason why we actually dedicate 8+2 OSTs in RAID 6, because that's how many drives we have in a physical OST volume group, is 10 devices. So that means you need more OSTs to create that RAID 6 8+2. Now in a grid RAID implementation, you actually consolidate the number of OSTs by 1/4, but still write 8+2 and distribute the sparing blocks. That means you actually have more sparing blocks available and more ability to leverage the efficiencies of disk drive capacities than leveraging RAID 6. And then overall, the number of OSTs managed in a file system is reduced by 1/4 with grid RAID, without sacrificing data resiliency in that regard as well. And then the other thing with RAID 6 8+2, in our configuration, you have 2 global hot spares shared for every HA partner pair in Lustre OSS. That means that anytime you actually have a failure, you only have 2 drives shared against 2 controllers. In grid RAID, each grid RAID has 2 sparing blocks, so essentially you could think of it as the HA partner pair has basically 4 global hot spares distributed across 2 grid RAIDs. Thank you. Any questions?
So John, as far as performance penalty, what reasons are there not to do this?
So our implementation of grid RAID compared to benchmarking in IOR is we demonstrated no performance penalty in terms of standard application benchmark compared to RAID 6. So really from our perspective, this is going to be a requirement when going to 6 terabyte drives, larger terabyte drives, that grid RAID is going to be essential so you're not spending hours or days trying to repair larger capacity drives. And a grid RAID, which is a cluster, Xyratex implementation of parity clustering, is actually going to be, I think, a hard requirement for a lot of our customers moving forward of how do we reduce the amount of rebuild rate without sacrificing front-end performance. And then overall, if you compare a pristine file system using grid RAID or RAID 6, performance is up to par.